So, having established that if we're going to study the entire universe, we're going to assume that we are studying a homogeneous, isotropic place, we are going to try to understand what that tells us about the nature of general relativity in a space that is isotropic and homogeneous. And so the first thing we need to ask is, what does this tell us about space-time? So what kind of a space-time describes a universe in which space is homogeneous and isotropic at all times? And it turns out that in the context of general relativity, isotropic and homogeneous means that there is a particular set of coordinates that we can find in which the curvature is constant at every point. And this need not mean, by the way, just because a space is the same everywhere, that it is flat. In fact, I have drawn here, or someone has drawn here on the right, figures of three two-dimensional spaces which have the property that they look the same as observed from every point. These are three surfaces of constant curvature. The one on the bottom is, of course, the Euclidean plane. Its curvature is exactly 0, and this is a familiar space, and it's one of the properties of the Euclidean plane that it's invariant under translations. It looks the same from every point. It's invariant under rotations. It has no preferred direction. Over here at the top, we have a two-sphere, a two-dimensional surface given by the outside of a ball. This is again a universe, if this were our two-dimensional space, in which every point is the same as every other point. In this case of the sphere, this is obvious because of its invariance under rotations in 3 dimensions. You could just take this ball and twist it around, making any point the North Pole. The North Pole is not distinguished by anything, unless you're on Earth, in which case it's distinguished by the rotation. But the ball in itself has no distinguished North Pole. And this is a surface of constant positive curvature. And then over here is this saddle-like shape, which has the property that its curvature is constant and negative. It is far less obvious why it is that all points on this shape are the same as all other points, or why there's not a preferred direction. But there is indeed a notion of rotation in this hyperbolic plane that preserves all of the geometry. And so these, in fact, in 2 dimensions, are the only 3 examples of spaces of constant curvature. Any space of constant curvature is one of these 3. And in 3 dimensions, we live in a 3-dimensional space. So our space at any given time, it turns out, is one of 3 types of spaces analogous to these 3. It can be a space of constant positive curvature, which is a 3-dimensional extension of the surface of a ball. In fact, it's called a 3-sphere. If you could imagine a 4-dimensional ball, this would be the 3-dimensional outside of a 4-dimensional ball. And like the 2-dimensional outside of a 3D ball, it has positive curvature that's constant, and all points in all directions are the same as all others. There's a negative sort of hyperbolic version of the same thing, and then there's plain old flat Newtonian Euclidean 3-dimensional space. And space at any given time is one of these. How do we distinguish these? Well, here, remember, these objects are drawn as surfaces embedded. You're meant to imagine that ball sitting inside flat 3-dimensional space, because that's where we are used to thinking. Remember that I'm talking about the ball in and of itself. There is no inside to this ball or outside. There's any more than there is below or above the plane. Our universe is 3-dimensional. It's not sitting, as far as I know, inside any higher dimensional universe, though maybe in an optional talk we'll have that discussion about maybe it is. At the moment, as far as we know, it is not. So all there is the 3 dimensions. So what intrinsic property of these spaces can tell us about the curvature? Remember that it's the properties of the geodesics, the weird straight lines on curved spaces. And the easiest, sort of most beautiful distinction that the geodesics tell us between 0, negative, and positive curvature is that, geodesics in the plane are our favorite Euclidean straight lines, and they satisfy the nice axioms of Euclidean geometry. For example, the sum of the angles of a triangle is 180 degrees. On this saddle point, and it's not completely clear in this picture, but on this saddle point's geodesic, I'm going to exaggerate the effect, geodesics, in fact, diverge, which tells you that the sum of the angles of a triangle drawn on a space of negative curvature is going to be less than 180 degrees. On the other hand, on the sphere, clearly geodesics converge. Think about 2 lines of longitude leaving the pole. They meet again at the other pole. And so the sum of the angles of a triangle drawn on a sphere will in fact be larger than 180 degrees. But note that a very small triangle drawn on the sphere, or a very small triangle drawn on the hyperboloid, will appear approximately will have a sum of the angles which is very close to 180, because a small segment of anything looks like flat space. The order of magnitude that tells you how big a triangle needs to be before you measure a distinction between flat space and one of these curved spaces is the magnitude of the curvature, denoted here by R0. There is no curvature here. If R0 is big, then the curvature is large. If R0 is big here, this is a very curved sphere, which means roughly that the ball it's wrapping is rather small. So it's more curved. And so all of the positive constant curvature spaces that can possibly exist are not exactly all the same. They are all a three-dimensional version of the sphere, but of course they can have different sizes. And so space, that if you decide that space is positively curved, then space at any given time is given by the three-dimensional analog of a sphere, and then the size of the sphere can change. And as the size of the sphere changes, its curvature can change. A bigger sphere, as I said before, has a smaller curvature. You need a bigger triangle before you measure deviation from 180 degrees. Likewise, you can make this hyperboloid bigger or smaller, and a bigger hyperboloid has a smaller curvature. And if you look at the dimensions, it's the area of the triangle that determines the deviation of the angles. So if you make the sphere twice as big, the curvature becomes 1/4 the curvature it was previously. So we have these three types of universes. Positive curvature universes are closed, just like this two-sphere, in the sense that there is no way you can get, two observers cannot get as far as they wish from each other. If you try to go too far, you come back around the world and come back to where you were. This is not the case for the hyperboloid. The hyperboloid is clearly open and infinite. There's no way to close that. And the geodesics are diverging. And then we could possibly live in a flat three-dimensional space. If we live in a flat three-dimensional space, then it looks at least infinite and open. And so the meaning of this question mark will become clearer. So space at any given time in a universe that is homogeneous and isotropic is either positively curved with constant curvature, negatively curved with constant curvature, or flat. And our job will be to determine which of these three situations obtains in our universe, and if it's not flat, then to determine the actual curvature, R0. Now, the space-time geometry of a space-time that at any given time is given by one of these kinds of spaces was described by a whole collection of people: Friedman, Lemaitre, Robertson, Walker, and it goes under the name Robertson-Walker geometry. Robertson-Walker geometry is the geometry of a space-time. So now we're talking about four-dimensional space-time, in which space is homogeneous. So at any given time, space is, say, a three-sphere, but the size of the three-sphere can vary with time, and so there is a scale factor that relates. Pick the size of one sphere to be 1, and then bigger spheres will have a bigger than 1, smaller times when space is smaller will have a smaller than 1. And because all we're doing is scaling all of space, the distances between observers that occupy, in some sense, a fixed position on the sphere, pick a point on the sphere and then stay at that same point when you enlarge the sphere, the distances between observers sitting at fixed points on this fixed space, so label points of space by observers, and then distances between them will all scale together when I make space bigger. And by convention, we choose the scale factor A, normalized, so that A at t0, which we call the present, is 1. In other words, d0 are the distances at t equals 0. And then if A at some future time is 2, that means that by that time, all distances have doubled, and so on. Now, in this Robertson-Walker geometry, you can solve the equations of electromagnetism, for example, and you find that light moves, and this is not an obvious fact, but it's true, despite the fact that space is growing, light moves along geodesics. In other words, the motion of a light beam is along these straightest straight lines that you can draw in space. If space is flat, light moves simply along straight lines. If space is a sphere, light moves along great circles, and so on. And it moves, of course, this is a physical obvious fact, with velocity c as measured by any observer anywhere. So any observer measuring the motion of a light beam in their vicinity will measure, of course, the speed of light, because that's the universal property. We're talking about a relativistic theory. And put these two together, you find that these spaces exhibit the kind of cosmological redshift that we already discovered underlies the Hubble discovery. In other words, light that it is emitted from some position in space at some time t, and is emitted as observed by an observer at that event with wavelength lambda emission, will then be observed at certainly some later time, obviously, because emission always precedes absorption or observation, and the ratio between the observed wavelength and the emitted wavelength is the ratio of the scale factors. In other words, it is a property of the equations of electromagnetism, and we'll see an example of this much later of how this works out, that as a light beam travels through space-time, if space itself is being scaled by some factor, then the wavelengths of light scale by exactly the same factor. And this gives rise to the cosmological redshift. If A is increasing, then the wavelength at which you observe something at a later time is larger than the wavelength at which it was emitted. This gives you the cosmological redshift. Note, this is not a Doppler shift. This is the Doppler. This is the redshift as observed by observers and emitters and absorbers that are at rest. If there are peculiar velocities, there will be a Doppler shift on top of this. But these are observers that are, as far as I can discuss, at rest. They sit at fixed points in the space, and it is the space, if you will, that is growing. And so it does not require any motion, and I don't want to think about it as a Doppler shift, and in particular, it is never a blue shift unless space is shrinking. It is indeed a gravitational effect, but it's a little bit different from the gravitational redshift we saw in the Pound-Rebka experiment, because in the Pound-Rebka experiment, again, we had a redshift when light was propagating up, but a blue shift when light was propagating down. In this case, in some sense, in an expanding universe, all light is propagating up. There is only a redshift. In a contracting universe, all light is propagating down. There is only a blue shift. But if we're both in the same, say, expanding universe, and A sees B's light redshifted, then B will see A's light redshifted, because in both cases it takes positive time for the light to get from A to B, or to get from B to A. How does our observation of the Hubble expansion fit into this framework? Well, we have our scale factor, which describes the scale of the universe at time t. It's a function of t. And for times near to the time t0, which by convention, remember, is the present, I can approximate this by a linear function. I can approximate anything by a linear function. And I will call, so it's 1 when t is equal to t0. This is its first order deviation. We're going to skate very close to calculus this week. I'll try to be as clear as I can when we get close to there. And I'll designate the coefficient by the letter h0. And again, this is expected to be valid in some kind of Newton approximation when this coefficient is small. I'll justify calling it h0 in a moment. In this case, by our cosmological redshift understanding, if light is emitted at some time before t0 and observed by convention, when I observe something, I'll be observing it at the present at time t0 unless I indicate otherwise. And so the wavelength at which light is observed divided by the wavelength at which it was emitted is the ratio of the scale factors. Here should be A of t0, but A of t0 by convention is 1. And what is this? This is 1 over the scale factor at t emission. So it's 1 over 1 plus h0 times t emission minus t0. But because this number is small, I can use Newton's approximation. This is 1 plus h0 times this inverse. This is, with Newton's approximation, the same as 1 minus h0 t emission minus t0. And 1 minus h0 times t emission minus t0 is the same as 1 plus h0 t0 minus t emission. So this is the expression that I'm going to use. It's valid when when h0 times t minus t0 is a small number. And so to this order, I can set 1 plus z equal to that. In other words, z is equal to h0 times t0 minus t emission. This is, remember, a positive number. T emission precedes T0. So this is the redshift. On the other hand, to the same order, it'll turn out that the distance light traveled is the speed of light times the time it was traveling. This will not always be true because the universe is changing. We'll see how that gets corrected. And so comparing this expression to that expression, I find that indeed I obtain the Hubble relation as a low-order Newton-type approximation at small distances and times. Small relative to what? To the distance light could have traveled since the Big Bang. Time small relative to the time since the Big Bang. And at those distances, and therefore redshifts small compared to 1. And under those circumstances, I find the Hubble condition. And so the Hubble constant is the coefficient of this expansion of the scale factor. That's the Hubble constant h0 because it's the Hubble constant today. The Hubble constant need not, in fact, be a constant. At any other time, I would define the Hubble constant, erasing all my scribbles, by if you have a time t star. And for times t not too far from t star, the scale factor is given by the scale constant at t star times 1 plus some number times t minus t star, then I would designate this number as the Hubble constant at time t star. So now imagine, if you will, that this expression is in fact correct. It's not an approximation. It's an exact equation, as we might have mistakenly thought last week. Then what does this tell me about the Hubble constant? Well, you'd think the Hubble constant's not changing. Look, this equation always holds. Yes, but remember the Hubble constant is the coefficient of the fractional change in A. So take some later time, and notice that in a given time interval after that, for every second past t star, the scale factor increases by the same amount. But if t star is later than the present, it's later than t0, then A by that time will have grown. And so the Hubble constant, which is the rate of relative growth of the scale factor, will in fact have decreased. So if you want to understand constant expansion to mean this equation where the scale factor is a linear function of t, then that in fact means a decreasing Hubble constant. In particular, we have no reason to assume the Hubble constant does not depend on time, and understanding its time dependence will be something we'll spend some work on to find out what it does in our real work. So, in our real universe. So, this is how Hubble fits into Robertson-Walker as a first approximation to the actual cosmological redshift. We said that one of the issues in a universe where distances are changing is what do you mean by distance? So we will have 3 at least different ways to define the distance between 2 points. One is, remember, we have these co-moving points. And so we label each point on, say, the sphere by some name, x, and then the distances are the distances between the x's. And then at previous times, we had the same sphere with the same points, except we considered all sizes smaller. And in the future, we'll have the same sphere with the same points, but all sizes are bigger. And so the distance along the canonical sphere is d0. This is the coordinate distance, we call it. You might think of that as the distance right now, because right now the scale factor is 1. So if you want to define something that measures the actual distance between two objects right now, and in particular will reduce for objects that are near enough for me to make a measurement for my right hand and my left hand, if you ask what's the distance between my right hand and my left hand, if you apply this crazy Friedman-Robertson-Walker coordinate system, then this will be measured by the distance in coordinates between the coordinates of this finger and the coordinates of that finger, evaluated at the scale factor 1, which corresponds to right now. Okay. But it's very rare that we want distances between objects that are very near, and in general, the coordinate distance between those two things is not going to be a physical observable because you cannot have time to lay a ruler a large fraction of the size of the universe before the universe changes on you. So what can you actually measure? Well, one thing we measure that is associated to distance is we measure the small angle formula. We love our small angle formula. So imagine that somewhere out in the universe is a galaxy, say, and the galaxy has size d. And the galaxy is at coordinate distance, d0 from me. So imagine that we're in flat space in a flat two-dimensional universe. So this is the universe at present, and here is the galaxy, and the galaxy is at a distance d0. Okay? Now, suppose that I want to make a small angle approximation and measure the apparent angular size of the galaxy. everything works fine. Remember, light moves in straight lines in this coordinate plane. That was our assertion, and that's the facts about Robertson-Walker. But, however, when I look at this galaxy, remember, I am looking at this galaxy as it was a long time ago. And so, in fact, the distance that I am looking at, if you will, is not the size of the galaxy itself, but in fact, the size of that galaxy as it looks in today's coordinates. So, in other words, that galaxy is sitting at a particular point in the plane. This is a measurement made in today's plane. However, the two sides of the galaxy in today's plane, the galaxy, of course, doesn't expand because it's gravitationally bound. We'll talk about that. But had I put 2 points at the two sides of the galaxy, they would have been much bigger today than they were then. Therefore, the distance between the two sides of the galaxy in today's coordinates is the size of the galaxy times the ratio of today's scale factor to the scale factor at the time of emission. And if I measure a redshift z for the light, then the ratio of the scale factors is 1 plus z. In other words, everything looks bigger in an expanding universe because it looks as big as it would have looked had its two edges expanded with the universe. That gives me this expression for the small angle formula. I define an angular size distance by angular size distance is the distance that you'd put in the small angle formula if you wanted it to make sense, if d over d were alpha over 1 radian over 206,265 arc seconds. And then from this expression we see that the angular size distance is related to coordinate distance or physical distance today by the expression, take that, divide by 1 plus z, where z is the redshift at which you observe the light from the object whose angular size you're measuring. Of course, for nearby objects, z is 0. This is the same old small angle formula. You don't have to change your understanding of the dimensions of the moon. But for distant objects, this is what the expansion of the universe tells you. You measure an angle that is the angle that you would have seen were the two sides of the objects freely moving and freely falling and expanding. So this is one notion of distance. There's another equation in which we use distance a lot. One was the small angle formula. The other, of course, is the brightness equation. B is L over 4 pi d squared. Which d should we plug in if we have an object of known luminosity and we measure its brightness? To what d does this equation correspond? In other words, for what definition of d does this equation hold? Is it d0? Is it dA? It turns out it's none of the above. It's something we call the luminosity distance, and let's compute the luminosity distance. So what really happens is that, 4 pi to radians is 4 pi. But if you have an object that's at a distance d0 in coordinates, then of course you find d0 squared here. However, remember, this is the energy that the object emits per second. Now, all of those photons that the object is emitting are getting redshifted. That means every photon that gets emitted, I am observing with an energy that is less than it was emitted with. And so that means, and the factor is the ratio of the scale factors, so that means that brightness is less than you would have expected at that distance by a factor of 1 plus z because of the redshift. Furthermore, if the object is emitting, say, 1 photon a second, and I am observing those photons, they're coming in redshifted, they're also separated by more than a second, because the redshift means that all times are dilated in the past. So there is the photons are coming less frequently, and each carries less energy. That gives me a total of 2 factors of 1 plus z. And again, this is something you can do in a slightly more rigorous way by a relativistic calculation. But this is exactly the logic that applies, so that the luminosity distance is given by the distance that you put in the denominator that relates brightness to luminosity. It has 2 factors of 1 plus z in it. And so I have 2 different definitions of distance that agree, of course. They're both d0 at small distance, but the luminosity distance is d0 times 1 plus z, because its square is d0 times 1 plus z squared, and the angular size distance is d0 divided by 1 plus z. This means objects appear dimmer because of redshift than they would, and this means that objects appear bigger because of redshift than they otherwise would. And so the bottom line is, since we can't really measure this, but we can measure sometimes both this and this, they are related by 1 plus z squared, a relative factor, and this sometimes you can measure. You can use that to verify that we actually live in a Robertson-Walker universe. Furthermore, there's another property, which is, okay, z tells you what happens to spectral lines emitted by a star. A spectral line emitted from a star at a particular distance will be redshifted by the redshift appropriate to that distance, given the distance redshift relation. What happens to the continuum blackbody radiation of a star? Does a star, of course it'll all be reddened. So the light that the star emits in blue might appear as yellow. The light that it appears as yellow might appear as red. What kind of a weird spectrum is it? This is beautiful. It turns out that the black body, the Planck black body spectrum, has the wonderful property that if you take every wavelength and multiply it by a factor, so stretch out all the waves by some factor A, it's still a black body spectrum. But it's a black body spectrum corresponding, of course, to a different temperature, and you wouldn't be surprised because of Wien's law that lambda max is 0.0029 meter divided by the temperature in Kelvin, that if all wavelengths get stretched, then the temperature, all wavelengths get larger, the temperature decreases by the same factor as the factor by which wavelengths increase, and indeed, a redshifted blackbody spectrum is a blackbody spectrum with a temperature that is decreased by the same factor by which wavelengths are stretched. This will play a role. So a star viewed at large redshift looks like a star, but a redder star. And you have to be careful when you're doing color magnitude diagrams of clusters. If they're far enough that the cosmological redshift is non-trivial, you will find that this is a meaningful correction, and you'll have to take it into account. Now, one more thing about the kinematics of relativity. We talked about the redshift that tells you that all clocks run slow. That was the second factor of 1 plus z. The coordinate factor, velocity of light. I said light moves relative to every observer with speed c. This does not mean it moves with speed c as observed in our coordinates, which means light beams moving in the dim distant past move with velocity c relative to the observers back then. Those observers have slow clocks and small distances. It turns out that in terms of the positions today of the observers that observed the light a long time ago, the coordinate velocity of light is actually not the speed of light, but it does move along geodesics, along straight lines. And then what about things that are not light? Well, do they move along straight lines? We observe that they do, and indeed, even along long distances, it turns out they do. Massive objects, just like as the case for light, they move along geodesics of space, so they move in straight lines, or whatever the straight lines are in your curved space. And it turns out that if the objects are freely falling, in other words, if they're only moving under the influence of the gravity, not something orbiting a star, I mean, they only move under the influence of the generalized gravity of this homogeneous space, the curvature of this homogeneous space, not the local fluctuations that are little galaxy clusters. We're averaging over all that. An object that moves only under the generalized gravity of all of space moves with a peculiar velocity that decreases as space expands. In other words, the peculiar velocity of a galaxy we observe means that in the past it was moving twice as fast when the distances between galaxies were half what they are now. So if we observe galaxies to be moving at all, it means in the past they were moving quite a bit faster. Remember, most of the peculiar velocities we observe are actually not freely falling velocities. They have to do with the orbital motion of a galaxy within its cluster or something. But if you look at the relative motions of distant large clusters that have nothing to do with gravitational orbital motion, then they will have moved faster in the past than they are moving now. And this is the analog of studying kinematics. We have described Robertson-Walker geometry, the geometry of a expanding or changing in size homogeneous isotropic space. And now what we need to do is figure out, what do Einstein's equations tell us? If you have some distribution of energy and matter, what does that do to the time evolution of space? So the curvature of space, the density of matter, and the evolution of the scale factor are all related by Einstein's equation, and that's the next thing we're going to turn to. Another thing to note is that all of these solutions to Einstein's equation have the property that they have a Big Bang, in the sense that at some time the scale factor becomes zero when you solve Einstein's equation, or if you want, at some time all the distances become zero. But that could be a question of how you measure distances. Remember, distance is an ambiguous thing. What's the unambiguous thing? At some time there's a singularity, all the curvatures diverge. They diverge either very far enough into the past, that's what we call a Big Bang. In some, you can construct solutions that don't have a singularity in the past, but then they have a singularity in the future. If you want to be creative, you can construct solutions that have singularities in the past and the future, but there are no solutions without singularities, so we're going to have to address this issue of the Big Bang at some point.